So it's time for our last convergence test here. Now we have the ratio and the root test. So let's explore a little bit here. Now I've got some sequences here, and we want to find the value of a sub n plus 1 divided by a sub n. And we're going to take the absolute value of that. So let's see what we get. So the absolute value of a sub n plus 1 divided by a sub n is going to be, well, we have 2 to the n plus 1 divided by n plus 1 factorial divided by 2 to the n over n factorial. All right, and we're dividing fractions, so as we know, we can multiply top and bottom by the reciprocal of this, or just rewrite this as multiplying by the reciprocal. A whole lot easier to work with. To the n plus 1 over n plus 1 factorial times the reciprocal of that denominator. And, well, I think we can clean this up a little bit here, right? Because here we have n plus 1 factorial and n factorial. So n of these are going to cancel out, the n times n minus 1. All of these are going to cancel out with most of these. All that's going to be left is n plus 1 on the bottom. And what about the 2 to the n plus 1 over 2 to the n? We'll subtract the exponents. 2 to the n plus 1, so n plus 1 minus n is just 2 to the first. So we get a pretty simple fraction. Now we're going to probably skip this step here and just realize that when we're dividing, we'll multiply by the reciprocal of the denominator there. So you might want to pause it and try that out. You can try these couple, see what you get. Let's see what we can get here now. A to the n plus 1 divided by, or a sub, I should say, n plus 1 divided by a sub n. Well, that's going to be, all right, you got to be careful here. The n plus 1 version, so we got to plug in n plus 1 for all the n's. So when we plug in n plus 1 here, we're going to have n plus 1 squared. We're going to have n plus 1 plus 1, which is n plus 2. So we got n plus 1 squared. We have 2 to the n plus 2 all over 3 to the n plus 1. Now we're going to divide by a sub n, which is just this expression. Dividing by this expression is the same as multiplying by the reciprocal. So let's just go ahead and multiply by the reciprocal. Okay. And now we should be able to clean a whole lot of this up here. So we have the n's will simplify, subtract exponents. So when we divide with the same base, we subtract exponents. So n plus 1 minus n gives us 3. 3 to the first, that is. Same thing here. If we subtract these, n plus 2 divided by n plus 1, that's just 1. We subtract the exponents, so n plus 2 minus n plus 1. And then we have these powers. We've got n plus 1 squared divided by n squared. Now be careful. We can't really do much with that. So we're going to have to write that as n plus 1 squared over n squared. Because this is really n squared plus 2n plus 1, and this doesn't cancel. So we'll just leave it like that. That's good. How about this one? A sub n plus 1 divided by a sub n. So the n plus 1 term is going to be n plus 1 to the n plus 1 power all over n plus 1 factorial divided by the a sub n term, which will be multiplied by the reciprocal. So we'll have n factorial over n to the n. Okay? And simplifying this up, if we cancel out n of these terms, then from n all the way down, that product will be canceled out, and that'll leave us with n plus 1 on the bottom. And again, these don't quite match, so we can't do much with them. So let's just, we're going to have to write it out into the n plus 1 to the n plus 1. Now, if we take a close look here, notice we got n plus 1 here and n plus 1 to the n plus 1 power. So that's the first power there. So we can subtract those powers because we've got the same base, n plus 1, subtract these. N plus 1 minus 1 is n. So we're going to divide, which subtract exponents, leaving n plus 1 to the nth, all over n to the n. Okay. And which, by the way, we could write as, we'll use this in a second, n plus 1 over n to the nth power. So that's some ratios there. And that don't mean too much to us until we bring in the ratio test. So here we have a new test. This is called the ratio test. This ratio test compares consecutive terms in a series to determine if the sum will converge or diverge. And here's how this series or the ratio test goes. So we have a series. Now, by the way, this is an infinite series. It's implied. So we've got this infinite series of non-zero terms, and it converges absolutely if the limit as n goes to infinity of this ratio is less than 1. It diverges, so that's less than 1, so it diverges if the limit of the ratio is greater than 1, or if the limit is equal to infinity. Okay, infinity is not really a number, so we got to say this separately. But infinity, the idea is the limit is bigger than 1. And finally, the ratio test is inconclusive if it's equal to 1. That means we can't tell if it's diverging or converging. All right, so let's try this out. So we have these three series. Now we're going to take these sequences and put them in a series. Notice they're the same, okay? So we're going to use the ratio test on these. So we're going to take this ratio, and we're going to find the limit as n goes to infinity of a sub n plus 1 divided by a sub n. Now we already did the work up here, so we'll steal that from up top. We've got the absolute value of n 2 over n plus 1. Okay, so this is equal to the limit as n goes to infinity. Now, 2 over n plus 1 is always positive because n is always positive here as we approach infinity. So we can drop those absolute values. Okay, so this is, well, as this goes to infinity, we know that the bottom's going to blow up, the numerator staying the same, so this is going to 0. So that implies by the ratio test that this converges absolutely because the limit is less than 1. So it converges absolutely by the ratio test. Okay. Well, what about this next one here? So let's go ahead and find the limit as n goes to infinity of a sub n plus 1 divided by a sub n. Okay. And let's use our work from up above. So we took this, same as this one here, and we found out that it comes down to 2 to the n plus 1 squared divided by 3n. Okay. Well, as this approaches infinity here, this is equivalent to the limit as n goes to infinity. This 1 doesn't matter there, so this is the limit of 2n squared. We can drop that 1 at infinity, or as we approach infinity. Oops, I lost this square here. That needs to be a square. N squared on the bottom, n squared on the bottom. So it's the same degree on top and bottom. Whenever we have the same degree, then the limit is going to be the ratio of the leading coefficients. Okay, 2/3 is less than 1, so this converges by the ratio test. Absolutely. Okay, and we got one more here. So if we find our limit as n goes to infinity of a sub n plus 1 over a sub n, okay, let's use what we got up above here. So this is n plus 1 over n to the nth. Okay, so we did all the work. We got our simplified version here. So this is the limit as n goes to infinity of n plus 1 over n to the nth. And now we're talking about at infinity, so these are all positive. We can drop the absolute value sign. All right. And now let's rewrite this. The limit as n goes to infinity of, dividing both these of n, this is 1 plus 1 over n to the nth. Now, this is a limit that we need to be familiar with. Okay, this is the definition of e, the natural number e. All right, so the limit of 1 plus 1 over n to the nth power is e. That's a limit that you want to kind of memorize. Hopefully you've seen that a time or two in the past. And that is obviously greater than 1, so this diverges by the ratio test. Okay, that's how the ratio test works there. So the big idea is we're comparing the next term or consecutive terms, and we're seeing what's happening as those terms go on. Will they continue to shrink in comparison, or will they be growing? So this is showing us that it's actually growing. The next term is going to be bigger than the previous term in a ratio of e. And so that will not converge. So let's look at the application of the ratio test here. So we want to find the convergence or divergence of this series here. Now notice this series has a fraction in it, so that's handy. So the ratio test says we need to find the limit as n goes to infinity of a sub n plus 1 over a sub n, okay, and the absolute value of that, okay, so the absolute value will take out this negative 1, right? So this is going to be the limit as n goes to infinity of the absolute value of the square root of n plus 1 all over n plus 1 plus 1, which is obviously n plus 2, divided by a sub n, which is the square root of n over n plus 1. All right, and I dropped the negative 1 because we're taking the absolute value there. All right, so this is equal to the limit as n goes to infinity. Let's clean it up a little bit. We got the square root of n plus 1 all over n plus 2 times n plus 1 over the square root of n. So what can we do with these here? Well, this is multiplication, so let's kind of swap these two, and this becomes the limit as n goes to infinity. And so we got the square root of n plus 1 over the square root of n. We could put that in 1 square root, n plus 1 over n. And then we have that times n plus 1 over n plus 2. And as n goes to infinity, this is going to go to just n over n, which is the square root of 1. And this one as well has a limit of 1. So that's times 1. So this is 1. So here we see that the ratio test fails because it is exactly 1. So when the ratio is exactly 1, it doesn't tell us either convergence or divergence. So this is inconclusive. Right? Inconclusive. If it's less than 1, we know it converges. If it's greater than 1, it diverges. But if it's equal to 1, we have an inconclusive ratio test. So we'd have to find something else to try to figure out if it converges or not.